Guys, welcome to this video on further work on differentiation. So in the previous video we've had a look at the idea of limits. In this one what we're going to do is we're simply going to focus on some further graph work. In particular we're going to look at some features of graphs, introducing a few bits of terminology, i.e. words that you need to have an understanding of. So we're going to have a look at the idea of continuity, this particular one here. Okay, so this here, what we mean by maximums and minimums, the idea of concavity, differentiability, and what's meant by the domain and range. We're also going to have a look at how the idea of the gradient to a curve, or at a curve on a point, at a point, can be found using something called the tangent line. So we'll use Graphmatica for a bit of that. We'll also hook back into these terms here. We're asked sometimes to find points or regions where a function is not continuous, so the idea of discontinuity, where maximums and minimums occur, where concavity of different types occur, where a function is able to be derived, and also how to describe the domain and range of a function. So they're the key objectives. Excuse me. Okay, let's have a look then first of all at this idea of discontinuity. Okay, so the key idea here is that if you have a normal function, okay, that's a terrible graph, let me try and redo that. Okay, so let's say we have a normal x-axis, normal y-axis, and let's just take a normal function like, say, y equals x squared. Okay, a rough sketch of that would look something like this. Okay, let's just go over it a bit more. Jeepers, that's terrible. Okay, what I'm going to ask you to do is imagine that that is basically a solid line. In fact, let's just retry that again. Okay, so we've got a very rough curve of y equals x squared. Now, what I'm going to, this idea of continuity or discontinuity, okay, the idea of a continuous function is a function where basically if you can draw the function without lifting your pen from the paper, i.e. there are no breaks in the function, we call that a continuous function. And in contrast, sometimes there are functions where there are points of what we call discontinuity. Like this example here. What we can see here, when x is equal to -1, there is a break in the function. Now this filled in dot up here means that when x equals -1, the actual y value isn't 1, it's actually 3. But it is a point where if you were to graph this, even if you went around that circle there and continued, at some point you'd have to lift your pen from the paper to fill in that filled in dot there. So there is a point of what we call discontinuity at x equals -1. If we move further on, we can see that when x is equal to 1, we've got this graph shooting up here, but then there is a break, and then to get the rest of the graph we actually have to lift our pen from the paper and start to draw this next part here. So at x equals 1 there's also a point of discontinuity, and there was one at -1. If we continue over to the right here, we can see that when x equals 3 there's another break in the function, so this is another point of discontinuity. Once again, we have to lift our pen from the paper to be able to graph this part. There's no vertical line here joining this. Okay, continue over here, another break in the function. So if we were to list the points where the graph is discontinuous, okay, we would have these x values that are given there. Okay, let's move on to the second concept, the gradient of a curve. So what we want to do here is we want to have a look at the idea that if we wanted to get the gradient, say at x equals -1, could I use this thing called a tangent line? So what I'm going to do is I'm going to jump over to Graphmatica and have a look at that, or this idea using Graphmatica. Alright guys, we're back here again, and what I've done is I've graphed this cubic function on Graphmatica, and here at the point where x is equal to -4, I've got Graphmatica to draw in this dashed line here. This is a tangent line. So, okay, first of all, what do we mean by a tangent line? Well, a tangent line is a line which touches a curve at just a single point. So this line here, this line here, just touches this curve here when x equals -4. And what we want to focus on is how do we find the gradient at this point where x equals 4. Now the gradient means, the gradient is the slope of a curve. So what is the slope of the curve at x equals -4? Okay, so one way of doing that is actually to use the slope of this tangent line here. Now, why would that be equal to the slope of the function at this point? So what we're going to do is we're going to zoom in on this point here. So I'm hoping that I can actually select part of the function. Let's retry that again. And let's zoom in on that. Okay, now what I'm hoping you can start to see is that the slope of the curve and the slope of the tangent, okay, as we zoom in, we might be able to see that they're getting closer and closer to one another around this point. So let me do a little bit more zooming in on here. Okay, this is showing it more clearly again. So this is the same function, we've just zoomed in a lot closer around x equals -4, and we can see that the curve, even though it's still obviously a curve, and the straight line, the tangent still a straight line around here, they're getting pretty much similar to one another in terms of their slope. So let's zoom in a bit more again. Okay, and as we can see even clearer here now, that the slope of the curve and the slope of the tangent are pretty much, well, they are the same around this point here. Let me just do one more zoom in. Okay, and that's basically showing almost as far as we can go with Graphmatica. Okay, that at this point here, the tangent line, we can just make that out as different from the curve, but at this point here, the slope of the two is the same. So, what we're going to do then is we're going to get the equation of that tangent showing up. I'm hoping I can actually do that. Let me just pause the video so I can get that equation back. Just a moment. Alright guys, back here again. So finally managed to get the equation of the tangent line up on screen here from Graphmatica, and what we can see is that the equation of the tangent line, okay, is 23x plus 127. Now from all that zooming in before, if I wanted to know what was the slope then at x equals -4, okay, it's going to be this value of 23, because that's the slope of this straight line when x is equal to -4. So the slope of the tangent at a point is equal to the slope of the function at that same point. So let's make that key point then. So the slope of a tangent at x equals, say, a is equal to slope of the function at x equals a. Okay, let's move on down to have a look at this idea of maximums and minimums. Okay, this is a relatively simple idea. A maximum is simply a highest point, okay, and a minimum is the lowest point. Now, you might notice in this little screenshot here that this is called the local maximum. Why is it called local? Well, you might appreciate that this function, if we continued it, actually would continue higher than this point here, and the function would continue lower than this, what's called the local minimum here. So the local maximum is the highest point in a particular region. So we can see that this is called a maximum point, but really it's, if we set it properly, it would be a local maximum. Okay, and this is a local minimum here. Usually we drop the word local off if we just talk about, okay, maximum and minimum. Okay, we don't actually need to put the word local in. So if we said, well, what is the local maximum or the maximum point? Okay, we would express it using coordinates, and this very roughly looks to me round about a half for x and definitely 3 for y. And the minimum point, okay, min for short, is not 3.5, maybe 3.25 or 3 1/3. Okay, what would that be there? Okay, I'm going to say that's around about, sorry for that folks, that's around about, I think, 3 1/3. So I'm going to say 3.3 comma -2 is the coordinates of that local minimum or minimum point. Okay, let's move on to the next part. Okay, concavity. Well, we've just talked about maximums and minimums. Okay, well, on a graph where you have this kind of curve situation, okay, what we've got is a region from about here to the left where it's basically what they call concave down. Okay, so it has that kind of shape to it. Okay, sometimes it's more pronounced, more symmetrical, but these are called concave down. Okay, then you also have regions like this one here. Okay, so just notice the cursor going over that there, which is called concave up. So this is concave, not concaved, concave down, and this is concave up. So if you're looking for concave down, it's like going into a cave, and concave up is the opposite of that. Now, they've labeled here this thing called a point of inflection. So what is a point of inflection? A point of inflection is where the concavity changes. So at this point here, okay, it changes from concave down to concave up. So a point of inflection is where the concavity changes. Okay, it's an important idea. Make sure you make a note of that. And make sure you clearly define what is meant by concave down and concave up. Okay, let's move on to differentiability. Okay, differentiability is basically saying, are there any points where the gradient is not able to be found? So differentiability means where are the points where you can find the gradient? Usually the question is asked though, are there any points where the function's not differentiable? So differentiability means you can find the gradient and where it's not differentiable means you can't. So when would that occur? Well, one point would be where the function is discontinuous, where we have this break. Well, why not? Why can't we find the gradient here? Well, the point doesn't exist here, so you've got to have actually a point to be able to find the gradient at that point. So you can say, well, what about this point here then? What's the gradient there? Well, how can you find the gradient of a point? Okay, it can't be found because you could draw tangents on every single side of that dot. Okay, so there is no defined gradient for just a dot. So points where the function's discontinuous would be where it's not differentiable. So we can say this particular function is not differentiable at x equals 2. But there's also another point, and it's this one which is highlighted here. Around this point here, you might notice that the gradient is a steady negative, suddenly changes to a positive value. So at this point here, at x equals 0, 0, we've got to ask ourselves the question, well, what would the gradient be there? In one moment, it seems to be a negative number and also a positive. So that sudden change in gradient, where it's basically in an instant, it is both negative and positive, which is what it can't be. We can simply say that at that point the gradient is undefined. Okay, so the function is not differentiable at x equals 0. Okay, and the last of these definitions, domain and range. Okay, we've got another piecewise function here. Now, what does domain mean? Domain is a mathematical term that means or refers to the x values that a function can take on. Well, you may think, well, can't you always have x values for every single point? Well, no. In this particular graph here, you might notice there's a hollow dot here when x is equal to 0. So there is no defined x value, sorry, there's no defined function value when x is equal to 0. So we would say that 0 is not part of the domain because the function is not defined at x equals 0. There's another point like that when x equals 1. Okay, what's the y value? Well, we don't know. There is no defined y value here. Now, what about x equals 2? Well, yes, there is. Even though there's a hollow part here, okay, the function is defined. It's equal to 1. So how do I write this? Well, we can say that x is all the real numbers. And here's a shortcut way of writing that. That is a funny looking E. It means element of. So x is an element of the real numbers, meaning all the numbers on the number line, but we're going to now exclude some where x is not equal to, though, okay, 0 and 1. Now, what is the range? Well, you might have guessed already that range refers to the y values. The y values that are defined for a given function. So if we have a look here, looks like basically this function, okay, doesn't seem to go below y equals 1, and that is true. Okay, so it's going down towards 1 here. It's actually equal to 1 here. Okay, and it's going down towards 1 here. Okay, so we can say, well, yeah, looks like the y value is greater than and equal to 1. Okay, and also notice this hollow dot here, okay, on both parts of this function is not defined, so a y value of 2 does not exist. So we can write y is an element of the real numbers where y is greater than and equal to 1 and y is not equal to 2. Okay, so y is any real number greater than 1, okay, but y cannot equal 2. Okay, so that's basically it. So make sure that you've got some a definition of continuity and discontinuity, how the slope of the tangent is equal to the gradient at a point, what we mean by maximum and minimum, what's meant by concave up and down, and also points of inflection. Okay, what we mean by differentiability, and when you can't find the gradient for a given function, and what is meant by domain and range. Alright folks, we'll see you tomorrow with some questions on this. Make sure that you note down anything that you're not too clear about.